Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on February 6, 2026, just 1 week ago. It reveals that while generic transformers often fail to grasp physical laws, acting merely as curve fitters, introducing specific inductive biases allows them to actually discover Newtonian physics. The paper is titled, From Kepler to Newton, Inductive Biases Guide Learned World Models in Transformers. And as we'll see later, the results for automated scientific discovery are really impressive. Figure 1 provides a visual roadmap of the entire paper. The top left shows the baseline setup, where planetary motion is treated as a next token prediction task on a discrete grid, a method that often fails to capture the underlying physics. The table at the bottom left lists the 3 inductive biases the authors introduce: spatial smoothness, stability, and temporal locality, to systematically fix these failures. Then, the large panel on the right illustrates the central discovery. It shows that with a full context window, the model becomes Keplerian, fitting a geometric ellipse to the entire history, whereas restricting context to just 2 steps forces it to become Newtonian, learning local forces and differential equations instead. Well, Figure 1 set the stage, and now Figure 2 digs into the root cause of the failure, the embeddings. Panel A illustrates that because standard tokenization starts with random initialization, the model must burn massive compute just to approximate a spatial map. In Panel B, we see this learned map is still broken. A continuous physical circle fragments into 4 disjoint clouds in the embedding space. Panel C quantifies this, showing an R² of only 0.86, which proves the model lacks the spatial smoothness required for real physics. So, while Figure 2 showed the failure, Figure 3 analyzes exactly what controls it, specifically vocabulary size and training data. Panel A demonstrates that with a small vocabulary of 100, the spatial map emerges rapidly, reaching near-perfect correlation. However, on the far right with 10,000 tokens, the map completely fails to form. Panel B quantifies this with a scaling law. The leftmost chart shows error dropping with more data, but exploding as the vocabulary grows, meaning large vocabularies effectively dilute the signal needed for physical understanding. Alright, since the previous figure showed the limits of tokenization, Figure 5 pits the classification approach against continuous regression. The left panel reveals a catch. Regression requires noise to work. The error curves dip at a noise scale around 0.1, confirming that noisy context is key to preventing error accumulation. Then, looking at the comparison on the right, the solid green line shows that optimized regression consistently outperforms the best classification models, in solid blue. Crucially, the dashed green line warns that without this noise, regression fails at large scales, which explains why prior research dismissed it. Well, to understand why that noise is so critical, Figure 4 visualizes the actual trajectories. The blue and green paths show the true orbit, while the red dots track the model's generated future. On the far left, where sigma is 0, we see the regression failure in action. Small errors compound rapidly, sending the planet spiraling into the sun. But in the middle panel, with sigma set to 0.1, the trajectory is stable because the model has learned to self-correct. Finally, the far right shows that excessive noise, like sigma equal to 1, degrades performance again, confirming the sweet spot we saw earlier. This brings us to Figure 6, which reveals the final inductive bias, temporal locality. In Panel A, the red bars show that restricting context to just 2 steps forces the model to learn Newtonian forces perfectly. In contrast, Panel B shows that a long context of 100 steps, the green bars, leads the model to learn global Keplerian orbital parameters instead. Panel C plots this phase transition explicitly, where increasing context switches the model from a physicist calculating forces to a curve fitter. Finally, Panel D explains the trade-off, showing that the Keplerian model's global view actually yields lower long-term prediction errors. So, while the previous figure compared the endpoints, Figure 10 maps out the transition between them. In the left panel, we see Keplerian scores rise as the context length increases from 2 to 100, meaning the model increasingly captures global geometry. Conversely, the middle panel shows the Newtonian scores dropping as context expands, so adding history actually degrades the representation of local forces. The summary plot on the right visualizes this crossover perfectly, with the orange Newtonian line falling as the blue Keplerian line rises. Wrapping up, the main takeaway is that without constraints, transformers act as geometric curve fitters. But by restricting their attention to the immediate past, we can force them to discover true Newtonian dynamics. This proves that building AI scientists requires deliberate architectural biases not just more data. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.